All right, so let's begin, right? Last day we did a summary on magnets. So let's do a few questions on magnet. Let's do a few more, and then we move on to electricity, right? Just about one or two again. Lastly, we did one on transformers, right? So hope you remember it, huh? All right, let's start with June 2021. June 2021, right? June 2021 number somewhere down here, 504 or something. Right, number 5. So figure 6 shows a DC motor, right? Which consists of a coil of wire ABCD between the poles of a magnet. The dotted line represents the axle about which the coil can turn. A current flows through the coil in the direction shown. So they give you everything you need, right? Draw the magnetic field between the poles of the magnet. So your magnetic field is somewhere to where? North to south, right? So do a quick little sketch now. Do a quick little sketch because we had to put a direction and thing on it, right? Do a quick little sketch. All right, so yeah, magnetic field moving from where to where? From north to south. Nice. North to south, right? Good. Steady direction in which state the direction in which side DA of the coil will move a current starts. What's the law we're using? Fleming's left-hand rule, right? Fleming left-hand rule, right? So use it there fast. The absolute direction that DA will move. What direction will DA move? Say using Fleming's left-hand rule, right? Try it quick. Right? First finger, north to south. Middle finger going from D to A. And the force is pointing how? Upwards. Very good. Upwards. Upwards, right? So the force will be upwards. What are you doing next? You guys using the rule? Oh, okay, okay. Right. Name the rule. Use the terming. What's the rule again? Fleming's left-hand rule, right? Write it out in words. Don't write FLHR, right? Write it out. Fleming's left-hand rule. Fleming's left-hand rule. Who's that there? Who's that right there? Tamara? Yeah. Tamara, come in front here, please. So I could check the work one time. Come. Right here. You got the booklet already? Where my booklet? Oh, look at it. But you don't need your phone. There's a calculator. Right, and explain why a split ring is used. What's the purpose of this split ring? To make sure current flows in the same direction all the time. All right. So the split ring is to make sure that current flows in the same direction all the time. You can take it off now. You wouldn't need them. What's the next one? They give you a little graph here. They give you a little graph showing an AC generator output, right? What's the value of the frequency? I just find frequency again. 1 over T. So your frequency here is 1 on T. What is the frequency? Take one. What's the frequency? Look at the graph. Sorry, what's the period? Sorry. What's the period from the graph? Period is time for one cycle, right? What you would say is the period there. No, just read it off the graph. This is one cycle, right? How long does that take? 0.02. So your frequency is 1 over 0.02. Right? How much is that? 50 hertz. Nice. So your frequency is 50 hertz. Right? That's your peak. 5 marks. Right. The peak voltage is applied to a generator. They give you the resistance. I know I didn't show you this as yet, but you have voltage, you have resistance, and you want to find current. What's the formula you're using to find current? I is equal to P over R. Are you okay with that? What was the peak voltage? The peak voltage here is how much? 200, right? So let's come back here and work out that quick. right? The peak voltage is 200 and the resistance was 100. So the current flowing is 2 amperes. Oh, anybody missing this some yesterday? I don't know if it went back. Wasn't corner there. Anybody went back? All right, I'll show it away, right? Next one. The generator is subsequently rotated at twice the frequency. What will happen to the period? So the frequency is now doubled. What will happen to the period? Right? How we know that? Look at the formula. 1 and 2F. Right? So that's a half. What does that mean? It means that the period is now half. Okay? Double the frequency means half period. What will happen on the other hand for the voltage? If you rotate it, yeah. What effect will this have on the voltage here? What do you all think? So if you move the coil twice as fast, will that change the voltage? It will most likely double it probably, right? But it will increase the voltage. Why? Whose law is that? Faraday's law. Right? Faraday's law. Hey, the AC come up there, you know, we have to play back one. Here, play back one. All right. Everybody okay with that? Right, nice. And you all said Faraday's law, right? Good. Right, there's one I'm looking for, but I'm not saying it. You gotta remember the question. We did it a few times as well. So I'm like, you gotta remember the question that we did with anyway, it don't matter. Let's do this one here. Jan 2018. Ready for part there? Complete the following diagram to show the magnetic field due to a current carrying conductor with it going into the plane. Draw the current going into the plane. All right, I give up. I can't find that paper. Right, current going into the plane is what? Dot or circle, dot or X. And you're using your right hand grip rule, right? So the current will be, sorry, the magnetic field will be, no, grip rule, right? This rule, left hand rule, is used to find force. Right hand rule is used to find current, right? Grip rule is used to find direction, right? So you will end up with clockwise. Are you okay with that? Now, question said, draw the magnetic field lines here. That's an X. Current going in. What's the rule you have to use to figure out the force here? Left hand rule, right? And then I showed you how to draw the field lines. Hurry up. That's it. Right, so if you use left hand rule, your magnetic field going from north to south, current going in, so your force is what? Left, right? Current going in, magnetic field north to south, so the force is downwards, right? Force is downwards. But remember, they wanted to put the field lines, right? So the force is down. So you look something like this. So look like that. Right? All the field lines pushing it downwards. Right? If it go upwards, you just switch the field lines around, right? Next part. X is what? Label X is a motor. X is what? X is the split rings, right? Split rings. Right? X is there, right? Split rings, right? Good. Explain when the switch is closed, how it will work. Right? And look at it here. They basically give you the order. Right? How to give the answer. Current direction, forces acting, rules applied, direction of rotation. Now continuous, how continuous rotation is achieved. Right? So you can use that as a guideline. Try it pass. I explained it to you yesterday. Try it now for yourself. Right? But try to take those exact things they tell you there and do it in that order. Figure out the current direction and so on, right? Make a note of the order, right? And I'm going back to the diagram for you. It's already labeled, so you're good to go. All you have to do is figure out current direction. Current direction, then figure out the forces, and then to the next part. Right. But try the explanation of it, right? You know, I got a paragraph, that's point four, right? First thing, right, sorry, direction. All right, we can go way to way. Right, from positive to negative, which is where to where? E to C, B to E, right? And then apply the rule, tell them what direction it's in, and then tell them which rule, tell them how you maintain continuous motion. Try to do it, please. You should have about 5 lines. Let me ask you. But the front here, you got current direction. What did we use in here? Seven class banner, right? Good. How is maintain continuous motion? Right, because of inertia, and then current going to receive that. Right, try and write it. Yeah, you know, how much you'll get. Right, at least answer each one of them, right? What direction it's flowing in? What are the forces? What it forces acting? What's the rules you use? What is the direction of rotation? And how is continuous rotation achieved? You should at least have 5 answers in. Right, and then we'll start electricity. Let's see how much you got. So number one, first thing, current direction. When you close the circuit, current will go this way, this way, this way. So current is flowing D to C to B to A. All okay with that? Next, you have to apply Fleming's left-hand rule, right? Fleming's left-hand rule. And if you apply Fleming's left-hand rule, your first finger going north to south, the current going D to C. So the force on DC is downwards, right? And therefore the force on BA will be upwards. So it is turning in a clockwise or like anti-clockwise? Oh yeah, sorry, that's down and up, yeah, clockwise. Sorry, right? So it's going this way, clockwise. Okay? You're going top going up and the bottom going down. So you're going in a clockwise direction. Say that. Right after that, how does it maintain continuous motion? Right? When the coil is horizontal, inertia will, because it's moving, inertia will pull the coil downwards. And because of the split rings, current continuously flows in the same direction. So therefore, the coil will experience the same forces in the same direction, causing continuous motion. That's okay? So that's all you have to remember. So number one, you have to remember current direction. Current moving D to C to B to A. Number two, you apply Fleming's left-hand rule. Fleming's left-hand rule, making it turn in a clockwise direction, right? How is continuous motion met? As it turns, when the coil is horizontal, inertia will pull the coil downwards, right? When the coil is horizontal again, because of the split rings, current will move in the same direction, right? Current will move in the same direction, and by Fleming's left-hand rule, the same forces are experienced. Okay? Yeah. Explain it. Right. You do it. Right? First finger, magnetic field, and current going where? D to C, right? So this finger have to go D to C. So your thumb point in what? Sorry. Yeah, D to C. So this finger have to point upward. Right? D to C, and your first finger going north to south. See enough? And if one is down, the next is up. Okay? So can you repeat what each hand rule is used for? The left hand rule, right? So let me just do a summary pass. Right-hand grip rule is to find magnetic field direction. Fleming's left-hand rule is used to find force. Fleming's right-hand rule is used to find induced current. Okay? Right, let's move away from magnets to electricity. All right, let's go to electricity now. First quick thing in electricity should be electrostatic, right? Right. Electrostatic, first thing is like a static charge. So a form of energy resulting from the existence of charged particles, such as protons or neutrons, either statically as an accumulation of charge or moving that's dynamically as current, right? So you have two charges, plus and minus, right? And negative charge, right? Electric fields move towards it. Positive charge, electric fields move away. That's okay, right? On like charges attract, like charges repel. That's okay. One thing I do, oh yeah, I have it here. Static electricity is stationary electric charge typically produced by friction, which causes spark crackling or the attraction of dust or air. Right? So we could obtain a static charge two ways, by friction or by conduction. Let's say you have a rod and you have a piece of cloth and you rub the cloth on the rod, right? Let's say the rod became here. Yeah, you can do that over, right? If the cloth becomes positive and the rod became negative, what does that mean? After friction, what does that mean? Right, the electrons from the cloth went to the rod. Will the protons ever move? No, only the electrons move, right? So the electrons move from the paper to the rod. Okay, that's friction. What about, sorry, not conduction? What's the word? Induction, right? So it's not charging by induction. So sorry, it's not charging by conduction. It's charging by induction. Here's how it works. Let's say you have a metal sphere, no charge, and you bring next to it a sphere that's positively charged. What will happen? The electrons will move towards the positive charge. That's okay. So one side will be negative, the next side will be positive. This is charging by induction. If I move this away, the charge is no longer there. Are you okay with that? So the two types of charging are charging by friction and charging by induction. I put the wrong thing there. Induction. Are you okay with that? Yeah, Josiah? Right here we have a simple circuit. Oh, by the way, current charges what? Charges current by time, right? Charges current by time, and the SI unit is coulombs. Are you okay with that? So that's the first relationship. Q is equal to IT. Right? Make a note there because we're going to run through all, right? Make sure you have them figured out. Always keep going back to this summary. Right now, since we know Q is equal to IT, it means that I is equal to Q1T. So current flowing in a circuit is the charge flowing per unit time. Are you okay with that? So if you have current flowing in a circuit, current is defined as charge flowing per unit time, SI unit, amperes. What's the alternate? What's the next SI unit for current? Charges in what? Charges in coulombs and time is in there's coulomb per second. Right? Always make sure you know more than one SI. Right? make it fine, right? Next, here we have a simple circuit. A simple circuit must have what? Right? It must have a supply, a switch, connecting wires and a load. Okay? So you must have those four things. Connecting wires, a supply, a switch, and a load. Every circuit must have that. These are all the symbols that we need to learn. Right? The ones that we tend to forget are what diode looks like, variable resistor looks like, and a fuse. Okay? Diode have a little triangle in it. The variable resistor have a line going through it. Right? And the fuse, what fuse looks like that. Right? What you call this here? You can see that. It's running through the battery. What do you think that is? A variable? Now, it will run into a cell with a battery. Right, so it is a variant supply. Right? Right, variant supply. Right, one missing. Huh? No, variant supply. So like if you have a 3 volts and you want to adjust the 4 volts, right? Right? That's a variant supply. Alternating looks like this, right? AC is this. Right? Make it, I think that's missing. So add this. Add in AC. AC is a little cycle in the middle. Right? Adding AC. Next, you have 2 types of supply. You have an alternating supply and a direct supply. What's the difference between both of them? What's the difference between an alternating and a direct? Right? In an alternating supply, the current is always changing direction. And the right, and the values also vary. That's okay? And the values also vary, right? Right? And as Soraya said, it takes a half cycle to change current, to change direction. So at one point in time, it's flowing clockwise, and next time it's flowing anti-clockwise. Okay? That's an alternating supply. All right? And the graph looks like that. Yeah? Direct supply, right? How do we go from alternating to direct? Well, partially. Rectification, right? Half-wave rectification, right? That's all we have to know. But to really do it, you need full wave, right? So you have alternating, you have direct, right? You have 2 ways that you could connect a circuit. You could connect a circuit series, parallel. How can you identify the difference between them? How you know a series circuit? Right? One continuous loop. Current only has one direction in which to flow. All right? So it's one continuous loop. Parallel, on the other hand, when the current reaches a junction, for example, here, when the current reaches a junction, it has more than one option. Right? It can flow up, or it can flow down there. That's okay? So it has more than one direction in which to flow. Right? Before I do IV characteristics, most important table here. Right? This table is very important for all the calculation. You need to know how current, voltage, and resistance behave. Right? So in a series circuit, current is the. In a parallel circuit, current is split up. Right? Voltage in series is what? Voltage in series what? Splits up. Voltage in parallel is the same. Look at that. Right? And I gave you the formulas for resistance in series and resistance in parallel as well. Yeah. So this table is the most important table when it comes to the calculation, right? Okay. Right. When they say now to plot the IV graph, this is the circuit that you'll always use. All right. A circuit must have a supply, it must have a load, it must have a rheostat. And you always connect the and a switch here. Well, this one don't have a switch, right? I should have a switch as well. Right? And your voltmeter is always connected in what? So your voltmeter is always connected in parallel and your ammeter is connected in series. Right. I don't have it here, but what about the resistance of ammeter? Is it high or low? Ammeter. Right? The resistance in an ammeter is low. Right? Because you want current to flow through it. What about a voltmeter? High. Right? You don't want current to leave the circuit and flow through the voltmeter. So make a note of that, please. Current in a voltmeter, sorry, resistance in a voltmeter is high, approximately infinity, real high. And the resistance in an ammeter is very low. Right? It's called low internal resistance and high internal resistance. So anytime you see a question said to draw and explain a circuit needed for IV characteristics, so the circuit you do it. Circuit is always the same. All that will change is the component in there. It could be a lamp, it could be a resistor, it could be a diode. It doesn't matter, right? That's okay? Right, so let's draw that circuit quick and I want to make sure you'll have it. Find this. G minus 3 minus and plus 2 minus 7. And also find this. Right. Let's see, find this. So now put this in the minus 7. Same thing you do it, put minus 7. All right, so your circuit will look like that. What you call this again? What you call this? Right, where resistor or rheostat? Why did you rheostat? Besides that, right, you need a fixed resistor for that. But why do you need a variable resistor? Right, to get multiple readings, right? So by adjusting the rheostat, you'll get different current and voltage readings. Then you can plot your graph, right? So make a note of why we have the rheostat. Right, the rheostat is used to, right, the rheostat is used to adjust the reading so you can get multiple, to adjust the value to get multiple readings. Right? So I will find G minus okay, nice. That is your IV characteristic. Okay, here. Right, so you must have your rheostat, right? All right. And these are two common IV graphs you have to learn: filament lamp and metallic conductor. Okay, by the way, what's the gradient of this graph? What's the gradient of that graph? Gradient is what? I over V, which is, remember, V is equal to IR, right? So R is equal to V over I. So what is I over V? 1 over R, right? So the gradient is 1 over R, right? So you have to flip it over. So the gradient of a I versus V graph is 1 over R. The gradient of a V versus I graph is R. Okay? So the gradient of a I versus V graph, 1 over R, and the gradient of a V versus I graph is R. Right, and these are all the formulas here that we need to know as well. V is equal to IR, right? W is what? What is called W? No, W is now what? W is electrical energy. Right? And P is power. Power supplied. Both of them here. Both formulas there could find power supply. Both formulas there could find power supply, right? W is electrical energy. Huh? Yeah, both by current, right? That'll be minus 21 plus minus 19. All right. You're gonna pass all the way around. Right, power loss. So if a question asks you to find the power loss is I squared multiplied by R. Okay. Power supplied is the other two. P is equal to IV and P is equal to B squared on R. Yeah. Let's go again. I gave you the circuit already, right? Right. When you're paying electrical bills, right? You have to remember that 1 unit is 1 kilowatt every hour, right? It's 1 kilowatt hour. So you're working in kilowatts and you're working in hours. Okay, so make a note of that, right? You're not dividing, you're multiplying kilowatts by hours used for. Okay, and well, I just remind you how to get that energy is power by time. Right, your power has to be in kilowatts and your time has to be in hours. Yeah. And last thing, electronics, a diode. A diode is what? A device that allows current to flow in one direction, right? So a diode could be forward bias or reverse bias, right? If the current is flowing with the arrowhead forward, it will conduct. If the arrow is going against if the current direction going against the arrowhead, reverse bias. When it reverse bias, no current will flow. When it forward bias, current will flow. Are you okay with that? So forward bias, current flowing, reverse bias, no current will flow. Half wave rectification is this. If you were to connect a diode to a simple circuit, all the negative parts of the circuit will not conduct, or all the positive parts. But in our example here, all the negative part of the circuit will not conduct. Right? So the circuit might look something like this, right? You have a supply, you have a diode, and the diode connected to a resistor, right? Actually, this should be alternating, right? So the alternating supply looks like this. All okay with that? When the current is flowing through the positive, let's assume positive going this way, the diode will conduct. So it will conduct in the positive parts. But when the voltage is negative, it will not conduct. So that's called half wave rectification. Yeah, all okay with that there? What's half wave? Everybody okay with that? So half wave means that the current will conduct in one direction alone, right? Michael, all good there? Yeah? Last thing, Vikash. The last thing is logic gates. These are your four okay. One missing, Vikash. Which one is that? Vikash, I'm missing a logic gate there. Not gate missing, right? So for all these gates, you have to learn the gates, input and output. Right? But to make it a little bit shorter, here's what you can do. Not gate is what again? One will give you a 0, will give you a 1 and a 1 will give you a 0. Right. Here's what you can learn. For AND gate, just learn that every time you have a 0, you're going to get a 0. Right? Look at it here. Every time you have a 0, you're getting a 0. Look at the OR gate. What's the summary for OR gate? A 1 will always give you a 1. So you just have to learn that. 1 will always give you a 1. And once you learn those two, you get to go. Because the NAND is the opposite to the, and the NOR is the opposite to the OR. Okay? How you know which one is which? How you know the AND and how you know the NAND? Have a little bubble in front. That's called the inverter. Right? So that there's a small inverter in front. Everybody okay with that? So everything all together is your electricity. Let's jump into it one time. Hello, what's your 1988? Oh? Yeah. Good, what's this? Please remember for the all-nighter, I expect you to know something, huh? Right? And I'll be focusing on the topics that you're having trouble with. Right? And then we'll be practicing all the others, but I'm focusing on those. All right? Yeah, I'll send the list just now. All right, let us start there. Why do I have 2022? Oh, yeah. Let's start with 2022. Number 6. Hurry up. Fill out that table there. Fill out the table. This is 2022, number 6. Wait, what you have to do? Some looking wrong there. Right? Nisha, how you doing? All right, let's go. Filament lamp looks like this. Next one, there's a what? A semiconductor diode. Fuse is what? Something like that. Yeah. Next one is what? AC supply. Cell looks like. Yeah. And last is a what? Rheostat, right? Or vapor resistor. A rheostat or a variable resistor. Let's go again. Oh, sorry. Anybody writing? All right, next one. So a manufacturer of popular cell phone has upgraded the battery to a capacity of 9,600 what? Coulombs, right? So they give us the what? They give us charge, right? They also give us coulombs here, but they gave us the charge. And they want us to find the time taken to charge it. Hurry up. So they give you Q and they give you what? Q1I, right? And they want to define T. Use the right formula, work it out. Go to online method your answers there. What's that? I. What's that? Sorry, Q1I. Work it out fast. Hurry up. What the formula would be used in series? We have Q and we have I series. What the formula we use then? Q is equal to. All right, hurry up. Q is equal to IT and make T the subject fast. You can do that mentally, right? Yeah. And then they give you power, find voltage. Online message answers there. Alia message something. Soraya message something. Colin. All right, so what do we have? Q is equal to IT, I is equal to Q over T. So that's 9600 over 0.8. How much you all got? 12,000 seconds. Huh? Oh, you're looking like an eye. Yeah. Yeah, it looks like an eye sometimes. Right, they want you to find voltage and they give it power. What's the formula we use here, Nikolai? They want you to find voltage. P is equal to IR. You sure? P is equal to IV. Hurry up, tell me what you got. Right, so V is equal to P over I. So that's 4.4 over 0.8. 5.5 volts, right? Easy, right? Nice and easy once you learn the little formula. Next, determine the work done. Determine the work done. What are you going to use? The work done to fully charge it. Huh? QV, I could work. Q by V. Q was what? 9600. And the V was probably just work out 5.5. Right? You could probably even use power divided by time. Plenty options. Yeah, work done is in joules. Energy is in joules. How much you got there? 52,800 joules. Lovely. Let's move on. Oh, done with that. Next one. You okay there? Next one, that was June. That was June 2022. '21 was the one that we did at magnets. June 21. What about Jan 22? I don't have that. Right, I have one in charge here. This is Jan 2021. Right, this one a little bit different, so let's see if we can figure it out. Draw the electric fields around each one. Hurry up. What kind of charge is that? Negative. Draw the electric field around it. Negative, positive, positive. Two plates here. Hurry up, start with negative. Draw the electric field, right? Electric fields move towards the negative or away? Towards. Right, so the first one is what? The first one is nice. Just make sure they're evenly spaced, right? And draw the arrows towards. Right, just make sure they're evenly spaced and draw the arrow going towards it. Yeah. Next, positive, positive. Positive, positive. Draw it fast. Yeah. Isaiah, you're coming on the board. Come now. Yeah. I see a puppy on there. Like charges, what? Like charges, repel. Okay, go ahead. Three of them going. Huh? Positive, positive is what? Repulsion, right? So they would repel. Huh? I'll probably draw one more out here if you want. Right? X is the neutral region, right? And they're moving away. Yeah, repulsion. So they won't interact, right? The field lines will just move away from each other. And the direction is important, right? And last part, sorry, well, next part here. See if we can figure out this. I want to pass around and watch your answers. You have a negative charge and a positive plate. Yeah, that's the thing for this one. Very quick, so you come up with. All right, nice. I've seen some good things there. Right? They will leave the it will leave the positive and go towards the negative, right? Huh? Yeah, all the field lines going towards the negative. There's a traction. Right, so that's attraction. So what would happen to that charge? It will be attracted upwards, right? The positive plate will pull it. Very good. Let's go again. Shivish. No, you're not good there. Come here, son. Come here. You're falling asleep. Yeah, that's message your mother. All right, sure, call the lesson now. Huh? Right, next part. Next part. If the number of electrons transferred from a charged rod to earth through a wire is, that's the number of electrons, right? You're seeing that? 4 by 10 to the power of 8. Write it down so we'll work it out. The number of electrons transferred from the rod to earth is 4 by 10 to the power of 8. So write down number of electrons is 4 by 10 to the 8. And the total charge is 0.64. And the total charge is 0.64 coulombs. Total charge is 0.64 coulombs. Calculate the magnitude of charge for 1 electron. How are you doing that? Think about it. Yeah, any ideas? 0.64, right, divided by, right? So the total number of electrons given at this charge here. So it's 0.64 divided by 4 by 10 to the 8. The magnitude of charge on 1 electron is 1.6 by 10 to the minus 9. Yeah? Same thing, right? 1.6 by 10 to the minus 9. Yeah, Isaiah, you okay with that? So the charge of 1 electron is 1.6 by 10 to the minus 9. which is not really true, yeah, but find the current that flows through the wire if it takes 0.4 seconds for all the electrons to flow. Find the current. What's the formula we're using here, Josiah? To find current, and they give it time. Right? So I is Q over T. Q is how much? From before, right? So that was 0.64 divided by time. 0.4. How much is that? Sorry? 1.6 amperes. Nice. State the direction in which charges will flow if the rod is positively charged. So if the rod is positively charged, what direction will the electrons flow? Right? What you all think the answer is there? The rod is positively charged, so electrons should move where? Well, the rod is positively charged now. So initially what? Right? The electron should have gone from the rod to the earth. Right? Okay, nice. Yeah. And last part. Explain how a static buildup of charges on a vehicle could be hazardous. How will it be hazardous? Right? How is the buildup of a charge in a vehicle? How could it be hazardous? How? It could get shot, but where is it? Where is it really hazardous? Right, but when you go to fuel up, right? If the nozzle were to touch the charged car, what will happen? Right, it could ignite the well, it could explode, right? So explain how the static buildup of charges in a vehicle could be hazardous, right? And what you will say is that in case of fueling, when the nozzle touches the charged car, a spark could occur. A spark could occur which would ignite the fuel and cause an explosion, right? Which would ignite the fuel and cause an explosion. All right, let's go again. Take it from one. Let's go again. right? So that is, what's that? Let's go again. What is absent for A? Tell them no, no. Please. After this one, I'll give you 2 minutes, right? So he would still messaging the thing. What are you doing? Still so long. Next one here. This is 2020, June 2020. Oh, no, sorry. Jan 2020, I think. Jan 2020. I'll give you a small break after this one, right? Very, very small. Hurry up. Logic gates. Complete that table there. Jan 2020. Complete that table. What do I have missing on top? Not similar to one. The one I'm missing on top, or not? Earlier, just choosing that from yeah. Finish? Finish, yeah? I'm just doing the first one, right? First one is a not gate. Oh wait, sorry. Wrong place. And gate. Functions. 2 ones will give you a 1. Right? 2 ones give you a 1, or you can say a what? 0 always give you 0. Anyone could work. All right. Or gate, you can tell them a 1 will always give you a 1. Well, in words, right? You're right, in words, right? One will always give you a one. NAND gate, straight back, inverter in front. Produces a logic 1 only when A and B are 0. Yeah, that could work. Everybody okay with that? Yes, sir. Next. With the aid of a diagram, with the aid of a circuit diagram, describe how an alternating current can be half-wave rectified. Draw the circuit pass. It's with the aid of a diagram. So you have to draw a diagram and do an explanation. Right? I showed you a little while ago. Try that there. Huh? That's IV. Halfway with the one that had like this, and then I had it like this. Right? That would have been about 5 marks alone here. With the aid of a diagram, explain how alternating can be half-wave rectified to produce a direct. We must in early now. Yeah, work it out, work it out. Right, so firstly you should have this. You should have an alternating supply. Right, you should have your diode. You should have your little switch here. And you should have a load and a voltmeter. Right? So you will show them that the voltage here is alternating. And what would the output here be? Half-wave rectified, right? That's the circuit you want to have. And that's the input and output you want to have. And you have to tell them what happened in words, not in your mind. Huh? What's that? Okay, I'll leave it in it. And then say in words what happened. Right, go ahead. Right? Give them a small explanation of how it works, right? Get a good diagram of a tree line. Right? A tree line. All I'm going to tell them is that the diode conducts current in one direction only. Right? When the circuit is turned on, the diode will conduct the positive. The diode will conduct in the positive part of the alternating cycle. Positive part of the alternating cycle. And the reverse bias is negative. Right? Remember, you want to put this in your own words, right? That's more unlikely what you remember. Right? So a circuit there, that circuit on top, giving you the input, and you're seeing what the output is. So a good diagram and you're good to go. For me now, that's all. When the circuit is turned on, the diode will conduct the positive part of the cycle and be reverse bias in the negative part. Okay, and diagram should all out. That'll give you a 5 marks, right? Sorry? Sketchy graph of the expected output real fast. That should be easy. You have it already, right? Yeah, that's the one on the end. Tell me what to do here now. I will do it. You just tell me what to do. Wait, let me pick on somebody. Chevy, shout me out here. Yeah, give me mine. Shavish, ready? Anyone? I take that one. Yeah, if you have to break after this, and you have one more. 5. All right, I'll run every 10 minutes. Let's do what last. All right, if you get it right, I'll give it. We'll get us 10 minutes. All right, yeah. Finish today. It's going up to what? And the period is how much? Yeah. Period is kaya right, so the period is 1/5, which is right, so it goes up to 12, comes back down, comes back up. Are you okay with that? So it goes up to 12, come back down to -12, period is 0.3. All right. All right. Take a small break, 8 minutes, and then we 8 minutes. So start back 12:25. I take a little small break and then we continue with this one. Those who don't want a break, I'll put the question up on the board one time, right? Please, what's up? What's I say? Yeah, that's all right. Right, we starting back 12:25. Man, that come to call them down.
Yeah, I can't have that.
Nobody. Did you do that? No, we have one child as well, extra. We have 2 minutes. I talk 9 cents. Yeah, 2 minutes. 2 minutes. I'm done, I'm done, I'm done. 1 minute, hurry up. 1 minute, I'll take in the cards. All right, right. Oh, man, is it up yet?
Serious amount of I think I will ever teach them imagine.
All right, time up. Guys, start.
Let's let them wait. Like it should be nice.
Come on, Clarissa. Let's start. Who is outside? Kevish. Kevish, all right, just start. All right, sorry they're online. Sorry they're online, I was muted, sorry. So the purpose of the fuse, right, is to help protect the appliance from a current value higher than its rating, right? So if you're rating 10, you don't want anything higher than 10. Earth wire. The earth wire is used to remove any excess electrons from the circuit, right? And the knowledge here. State 2 reasons why appliances that connected in parallel. Dylan, why? Why are connecting parallel? Parallel is for what? So what? Same voltage, right? So you make sure that the voltage supply is the same, so you don't need a large voltage supply. Right? What else? For independent control. Right? So you can control each one independently. The first one is to make sure that all the appliances require the same voltage. Right? Because voltage in parallel is the same. Second one, you allow for independent control. You allow for independent control. And what else? What else you can do with a parallel circuit? So if you have two appliances, right? And they both have different current ratings, how much fuses you'll need? Different current ratings. Two, right? So you need a parallel circuit to help you connect up the fuses, right? That's okay? So a parallel circuit helps you to individually protect the appliances as well. Part two, Samira. Part two was to remove the excess electrons from the circuit. To remove the excess electrons from the circuit. Huh? Hmm? From any circuit. Both of them from an. Next part. Find the total resistance. What's the first thing you have to do here? What's the first thing you have to do here with the circuit? Add up the? Nah, add up. Well, use the formula and simplify it, right? So take these two parallel and convert them into one. And then those three will create what? 1, 2, and 3. They'll create what? Huh? How you do that? Those three will create what? In series. All right? Hurry up, use the parallel formula and simplify the 4 and the 6, and then put them all together. Without one formula. Table on top there. How much you got there? 1 over R is equal to 1 over 4 plus 1 over 6, right? So you'll get 1 over R is equal to 5 and 12. So R is how much? 12 and 5, right? Nice. Okay. So we could take off those two. And we could take off that, And write 2.4 ampere. Sorry, ohms. All okay with that? So we convert the two parallel into one. And now 3 of them are in. Yeah? 3 of them are in series, right? So the total resistance is what? Add up the 3, the 2, and the 2.4. 7.4 ohms. Right, copy it down. Copy it down. Ya bola? Ya bola? Here too? Ni bola? Next part, find the total current in the circuit. Current is what? Yeah. The voltage was how much? 24. I is equal to V on R. So V is 24 and R was how much? Right, work it out. How much is that? 3.24 ampere. Right, read the next part. What do you think here? Right, which one are the integrated here you'll take? 4, right? Which one? 4 amperes, right? 2 is too small, 3 too small, and 4 just good, right? That was any questions online? Okay there. Let's go again. Right, remember tomorrow we'll focus on waves, right? Huh? No, I have a bit more. What's my not you me? Right, there's a next logic gives in John 2017. Did I do John 2022? think I'm missing that here. Huh? Are you John 2022? Guys, hurry up here. Hurry up. What are you doing? Twenty 17, Jan 2017. Yeah? What's that there? Arian, what's that there? And not Anna? And then Dana? Hurry up, fill out that truth table there. Huh?
To the icon on the creation of
Right, answer is what? 1-1 here. And in the last one is what? Right. All okay with that? Moving from there. Work out what is A, B, and C. Work out what is A, what is B, and what is C. The input there and the gate there. Just wait to figure out the output. Very easy. Oh, I forgot to pass on the list with you all right. Done. Yeah. Ready? Right. Do ABC for me, please. Nalia. A is what? Okay, cannot show enough. A. Any pen is working right now? Oh yeah, okay. Yeah, Nalia. A is what? By the way, those gates are what gates? A is what? 1. B is 0 and C is 1. So will the alarm sound? Yeah, the alarm will sound, right? All right, nice. Next one here, ABC, tell me what's the answer. Work it out. I'm better. I'll pick somebody up here. Sorry, I'm phone right you. Sorry, A is what? 1. B is what? You sure B is 0?
I don't know, but I.
Okay, sorry. Oh, yeah, one.
Because yours on your phone, you didn't say that one up on a turn. Right? A is 1, B is also, and C is 1. Right? A is 1, B is 1, C is 1. Are you okay with that? All right. What are 3 ways in which advances in electronics, such as the logic gates, have a positive impact on society? Yeah, 1. Right. So 1 has alarms, right, to help with security. 2 is what? To help with calculations, right? Help with communication.
Yes, seriously, smoke detectors.
Right, smoke detectors. What? Right? It's more logic games, right? So for security reasons, to help with calculations and different functions, and to help with what's the last one I said? Communication, right? Right, we can squeeze in one more there, man. No. Nah. Right? Yeah. Sorry? Nah, that good. What's the next? Did I get to do John?
Yes, it is. January.
No, I didn't do one 2022s. I don't have. Which one I didn't do? Jan 2022? Did I do Jan 2022? No liar. Yeah, I didn't have a good habit now. Jan 2022 is all the giveaways, magnets. But we can do it still, then. Yeah. So come back to it. Huh? Sorry? Jan 2022 and we done. We'll do it together, right? We'll do it together. Wait. Yeah. Right? You have a solenoid. How we gonna get the magnetic fields? What's the rule we're gonna use? Right? Grip rule, right? Tell me where the north is, left or right? On the right hand side. Good. Right? Current coming out at the top and going in and bottom. Right? Current coming out at the top and going in at the bottom. So to the right will be north. And then you can draw your field line. Right? Next one, the diagram below shows a constant magnetic field out of a surface as indicated by the symbol dot, right? So coming out. 7 and 8 shows a metal wire AB moving across the magnetic field in the direction shown. So you're moving a conductor in a magnetic field. What you'll get? You should get a what? you're moving a conductor in a magnetic field, so you'll get a current, right? So they give you all of that there. They show you how it's moving, right? Complete the table below by stating the direction and the magnitude of current. All right. Yeah. Last one, and we done. What will happen here? What direction will the current be on the arm wire? Right hand ruler using it? Yeah, you want to find current. So what direction is current moving in? You packing up? You're gonna get next one, girl. Right? This one is for you here, Elena. So figure it out. Yeah, what to do? Right hand rule, right? So your magnetic field coming out. So your magnetic field pointing out and the force is upwards. So the current moving from A to B. You all seeing that? You all seeing that there? Because watch, the thumb pointing upwards, right? Do it relative to the diagram they're watching, right? So your thumb pointing upwards because the force is upwards. And the magnetic field moving where? Coming out of the page. So the magnetic field coming out. So your middle finger point direction current. So your direction of the current is from A to B. Huh? No, because it's going up, but the magnetic field coming out of the page. So you have this finger to point out of the page. Right? So coming up and it coming out of the page. So what? If you're doing it there, the force going up, the magnetic field coming out. So your middle finger pointing from A to B. The middle finger, yeah, A to B. Right? Right. Last one and we're done. Elena, sorry. Do this one here. What direction current moving in? Right hand. Yeah, where you go? You wait on Elena to wrap up. Who has pack up there? Sarah? Yeah. Sarah, where? Oh, you all them pack up good out. Tomorrow, what you got? What direction current is? No, tell me A to B or B to A. Right? So your forces. The forces where? The forces towards me. What's the force? Right? Do it relative to the diagram, right? So the forces towards me. And the magnetic field is where? Out, right? So this finger pointed out of TV. So your middle finger going downwards. So you're going A to B. So you're going A to B. Okay, enough? So your force going, what's again? What direction the force moving in? Left to right. My thumb pointing left to right, right? What direction the magnetic field is? That's up, out to the TV, right? So you the middle finger pointing where? Down.